introduce you to Professor Winfried Hensinger. Hensinger. Okay. He's been at the University of Sussex for about 18 years or so, and he did his PhD at Queensland, the University of Queensland at Brisbane. He also spent some time in Michigan, and he's risen up to quite a good level now as a professor in quantum computers.
Technologies.
Yes, and technologies as well. I'd like to welcome.
Good. Yeah, thank you very much for the invitation. I think over the years I've been, I remember at least twice I've been speaking in this event, so I'm very happy that you invite me again. So what I'd like today is to tell you a little bit about quantum computing, how we go about actually building quantum computers. So I love questions, so plenty of time after the lecture for questions, so don't hesitate to ask lots of questions. I hope there's no time limit for that. If you have an urgent question, don't hesitate to put up your arm during my lecture. With that, maybe I'll just get started. So quantum computing is a wide term nowadays. So quantum computing is being done across the world with different hardware platforms, in different qualities and different what's the word? With a different size or specification. Now, what I want to talk about today is to build quantum computers that are not just interesting for academic study, but machines that could solve really important industry problems. And so that very much limits the way how you can build such a machine, and in a way makes it a lot more challenging as I'm going to show you today. So let's start with that, and maybe the most important thing I should start with is the real heroes who have made possible what I'm going to show you today. So this is my research group at the University of Sussex, and these guys, really incredible scientists who've managed to make some of these really amazing and mind-blowing breakthroughs that I want to show you today. Equally, I should acknowledge that what we do is extremely expensive and could not be done without the support of a whole range of different funders, all the way from US DOD to UK MOD to Innovate UK to European Commission's quantum flagship EPSSC, and also companies and all sorts of other entities and other universities. So with that, let me start by giving a bit of a general background. So this is how computing started. This is kind of the first computer, the first transistor, and obviously computers have become better over the years, much better. That's kind of expressed by Newton's law. Now, you make these computers better by making the transistors smaller and smaller, and eventually will approach the size of single atoms, single electrons, which is when it becomes much more harder to make computers faster. You all know that in the sense that Moore's law doesn't really operate the same way as it maybe operated in the first few years, and indeed Intel famously pronounced that maybe this is now the end of Moore's law. And you could interpret that as a problem, as a challenge, as a limit of computational technology. But good physicists usually seek opportunities, and a very good physicist, Richard Feynman, indeed pointed out that when you get to the world of the very small, then making use of the very strange phenomena of quantum physics, he can actually indeed build something that operates entirely different than the technology we are used to in our day-to-day life. And so maybe this was the first proposal of building a quantum computer. So let's start first with what is even quantum physics. Hands up, who has heard of quantum physics before? Good, good. Very, very mysterious. Who would agree it's a bit mysterious? Hands up. Good. So indeed it is very mysterious because an object can be in two different places at the same time. So I can be here and I can be sitting at home having dinner right now. So quantum physics in principle will allow exactly for that. During my PhD, I was lucky enough to spend through my PhD with a really, really fantastic scientist, Bill Phillips, at least in Gettysburg in Australia. And during that time, we managed to do an experiment where we made an atom move both forward and backward simultaneously. So imagine you park your car in a very narrow space, and rather than just hitting the car in front of you, at the same time you hit the car in front of you and the car behind you. So that's kind of like what also is can happen in quantum physics. And then obviously you've probably heard of entanglement. Einstein referred to it as spooky. He didn't like it at all, and in fact came up with a lot of ideas and thought experiments to kind of disprove some of the very strange concepts that sit below entanglement. So this is kind of the spooky, strange world of quantum physics. And a lot of scientists, including myself, spent many, many years trying to investigate it, trying to get a head around the strange laws of quantum physics and to observe some of these very strange phenomena. There was a point when scientists felt actually could we capitalize on these very strange phenomena and could we actually build machines that essentially make use of these strange phenomena to do something that is impossible with normal machines, with normal technology. And that is the birth of quantum technologies. And so today I'm going to focus on one particular quantum technology, and that is quantum computing, and tell you a little bit more about that. But in fact, there's a whole range of other technologies that also profit from quantum phenomena. So, oops, button. So what's quantum computing? It's a entirely new technology that has very little to do with conventional computing. But maybe one of the things it shares in common with quantum computing is the fact that it may evolve in a very similar development trajectory, and I'm going to get to that in a second. So let's start first with what quantum computers actually do, and they can solve certain problems where even the fastest supercomputer may take billions of years to solve. And more mathematically speaking, it changes the scaling of how long it takes to solve a certain problem. So just to give you a feeling of what are these problems, this is a good place to learn about the different quantum algorithms available. Is this website. It's called the NIST Quantum Algorithm Zoo, and you'll find there are a whole range of algorithms, and these include search, factoring, optimization, quantum Fourier transform, lots of different algorithms, and what does that mean in practice? Factoring algorithm can be used to break RSA encryption, which is the encryption we use nowadays to put your credit card details on the internet. So another application is trying to understand hydrogen fixation, which might help to make fertilizer production more efficient. 2% of the world's energy being spent making fertilizer, so you can imagine that process can be made a bit more efficient. That's a very significant effect. Things like understanding protein folding in biology, may help to find a cure for diseases like dementia. In general, the ability to understand our physical systems is very, very important. And maybe this is captured with the idea of simulating our quantum systems. So quantum systems are notoriously difficult to simulate exactly. And so usually what we do we have to use certain approximations in order to run such a problem on a conventional classical computer. But these approximations then also render these calculations often not so exact or not so useful. And so it's very important then to have a machine that could really solve the full quantum dynamics of a system, and that could help you in many different instances, for example, in understanding angular directions to create new pharmaceuticals. So now the million-pound question is, like, have we found all these amazing applications of quantum computing, and so I always like to answer this question with a historical equivalent. And so famously, Thomas Watson is said to have said that he thinks there's a world market for maybe 5 computers. And Thomas Watson clearly was a very competent man, so it wasn't just like some guy who didn't understand what he was talking about. But that was his genuine feeling, and I think it kind of reflects on the uncertainty when a new technology emerges, and this is also nicely expressed in this article. I realize this is written a bit small, so I'm going to read that. The electronics people said, actually I'll just read this. The electronics people said there were too many vacuum tubes and they would never run. The mathematics people said there were no problems complex enough that computers were needed. So I think this is great, and it really does reflect a lot, like how we're always naive and learn a lot when technology emerges. I don't think any of these people would have thought of the ticket machines at Brighton Station or the machine learning that allows you to detect cancer, all the things computers nowadays can do that you wouldn't even thought about. So how do you go about building a quantum computer? And building a quantum computer very much relies on the idea of superposition. But let's start first with conventional computers, and let's start first with how do we encode information into a conventional computer. And it is done using a string of zeros and ones in terms of bits. And so on a quantum computer, so a classical computer with 2 bits, you can now, for example, just write in this particular string 0, 1, and so imagine you have this very terrible memory stick that only allows you to save 2 bits. You've decided to write 0, 1 in there, then your memory stick is full and you're done. That's it. So imagine you have a quantum memory stick. And so now you can kind of work with the idea of superposition. Because this quantum memory stick also has 2 quantum bits, but because the quantum bit can both be 0 and 1 at the same time, rather than just being able to program in 0, 1, just like in the classical computer memory, you can simultaneously at the same time program in 0, 0, 0, 1, 1, 0, and 1, 1. So essentially you now have programmed 4 numbers into these 2 bits rather than just a single number. And that may not sound that very impressive. You could argue, okay, this is only 4 numbers rather than 1 number. So the best way to understand why this is a lot better than classical memories if you just go to 100 bits. So in a 100-bit memory, you can just program in 100-bit number. Then the memory is full. On the other hand, a quantum computer with 100 bits, you can program in all these combinations. I can't actually say that number, so I'm going to refrain at this point to the number. So this is all these different combinations that all simultaneously encoded into these 100 bits. And so in general, that's 2 to the power of n, where n is the number of bits. So that many combinations can be programmed in there. And so that kind of, in a very simplistic way, not quite the full story, but in a very simplistic way, gives you at least a feeling of why quantum computers are more powerful. So you've heard a lot about quantum computing, I'm sure, in the media, and you've heard there's an IBM quantum computer, and you've heard from Google developing quantum computers, and various different hardware platforms. So now we have quantum computers, and we've already done. Isn't why we're still standing here? Where are we actually with quantum computers? So maybe the best way to think of the development of quantum computing is the operating modes of quantum computers. And so there's two operating modes. One of them is called the noisy intermediate state quantum devices regime. In that regime, you don't correct for the inherent errors that occur when you do a computation. So no computations are perfect, there's always some inherent errors. And so this operating mode is very limited because you don't correct for any of the errors. That means the errors accumulate up and eventually render the quantum computer very quickly useless. So you can only do a very limited number of operations, and so the algorithms, applications you can cover are very limited. And that is where current technology really sits. So all the machines you've heard about in the media are sitting within that kind of this regime. So the much more interesting operating modus of quantum computers is what's called the fault-tolerant quantum computing operating modus. And in this modus, you correct for the inherent errors that occur within all the physical operations that are happening within the quantum computer. And what that means is, because in order to correct for these errors, you need a lot of extra qubits in order to enable you to correct for these errors. And rather than doing this with 100 qubits, you need 100,000s or millions of qubits. And so that makes this really difficult. So you have to build quantum computers that don't just hold 100 qubits, but actually millions of qubits. And if you are successful at achieving that, then you can indeed cover most of the applications that are known for quantum computers. And so there is multiple different platforms available, so one of them is superconducting qubits. That's you've probably heard about. That is used for in the machines by Google and others. And another platform is trapped ions, charged atoms or ions. And that's what we're going to talk about today. So the reason why we work with trapped ions is they're actually essentially a room temperature technology. And so when something operates at room temperature, that also means you have a lot more cooling power available. And so what is cooling power and why is that important? Cooling power is the ability to cool a large mass to a certain temperature. And so the more cooling power you have, the more qubits you can cool. And the more connections to these qubits you can cool. And the problem with superconducting qubits, because they operate at millikelvin temperature, it's very challenging to increase the system size to millions of qubits. And in stark contrast, because trapped ions operate only with mild cooling, it means you can scale this much easier to larger qubit numbers. And maybe something which is a bit more technical is the idea of cosmic ray errors that are inherent in superconducting qubit machines that lead to correlated errors, and that's kind of a big challenge because when these happen, you can't correct for these errors, and that makes it very difficult. So people have to put these superconducting machines in mines well on the Earth to shield them, and that becomes very, very difficult. So that's then showed why we use this type of technology. And here's a picture of a string of trapped ions in our lab. So each bright dot is actually one charged trapped ion. And so in order to explain to you how a trapped ion quantum computer works, I'll go over to consult with Tom Clancy, because actually in his best-selling book, he's actually within one paragraph managed to summarize the entire field. So I thought this is just great, and I'll just show you Tom Clancy's view. And I have a new laser pointer that has an amazing opportunity to. Let me try this. This is the first time I'm using this laser pointer, so But this is quite amazing technology. Here you go. Look at this. This is amazing. So, so what Tom Clancy says, you confine ions and webs of magnetic. That's very difficult, actually. I'm just going to read it like that. It's like very complicated. So you confine ions and webs of magnetic and electric fields. Hit a trapped particle with a burst of laser light, send it to an excited state, then hit again to ground it. That's your switch. Rows of ions in a quantum logical gate, giving you the smartest, fastest computer on Earth, neat, clean, and perfect. And surprisingly, this is actually a rather accurate description of quantum computing, with one exception, which is a blatant lie. The last line, if you come to our lab, it will certainly not look neat, clean. In fact, it's a big mess. So but the rest is actually surprisingly accurate. So how do you actually now encode information into single atoms? And the way we do that is to use the spin of an atom. So the spin, in a very simplified explanation, is the trajectory of the electron around the nucleus of the atom. You can think of an electron could have two different trajectories. These are represented by these two trajectories here, by the red and the black trajectory, and they correspond to two different energy states. And if I want to now, so if I want to now change the atom to go from this state to that state, I can send in radiation of a laser or microwaves to then change to the state of the atom. And as such, then now I'm back to my bit. So the 0 is the 0 of the bit, and the other state is the 1 state of my bit. And so that's already very good. The amazing thing now is that indeed I can be in a superposition so I can be both in the 0 and in the 1 state. So that's a kind of strange thing about quantum physics that is being applied now. But let me make one step back first, and I'll tell you how do we actually go about trapping individual atoms. And so what we need is an electric field. So the electric field essentially represents the force that charged particle fields. Now we need an electric field to essentially point from all directions into a single position. And that would be the ideal scenario. Unfortunately, there's a very stupid physics law which completely makes this illegal. So, but when physicists struck with such a problem, they always come up with a fix. And so this is the fix. So it's this kind of strangely oscillating potential. So, so imagine if I were to place a ball in the middle here. Do you think it would stick around, or would it roll off? So let's do a vote. Who thinks the ball, if I put it in there, would stick around? Hands up. Who thinks it will roll off? Good. That is very good. So here is the resolution of this little experiment we've done. So this is a saddle. You can see that thing indeed rolls off. So, but now what we're going to do is we're going to spin the saddle. And now you can see spinning oscillating potential just about holds this thing in place, and that's why we ended the film quickly before that actually comes off. Right, so it only comes off because there's friction. So if we didn't have friction, it wouldn't work a lot better. So how do we do that in the actual lab? So this is a vacuum system. And inside the vacuum system, there's really no air. So little air, actually less air than in outer space, as if you were to step out of a space shuttle in outer space. You have more air to breathe than inside this vacuum system. And that's obviously very important, because when we trap one atom, we don't want all the other atoms colliding with that atom, and so we need a vacuum. And so inside here sits a microchip, and inside, so you can see that microchip here. Right, there's that black spot there. And so you can see here you can also see the microchip zoom in of this microchip. And so the whole architecture looks like that. So you can see all these little squares. Each square is an electrode on the surface. This is a silicon microchip, and you see all these different squares. And by applying, as you can see the ball, the red ball up there. Yep. And so the ion now levitates above the surface of the microchip, and by changing the voltages we apply to each of these squares here, we can now change the electric fields. And by changing the electric fields, we can just transport the ion across the chip. And so essentially the ion now follows these roadways. So you can see these roadways here, and these junctions. The ion can go across around the corner as well. And by doing so, we can now execute a quantum algorithm. So that means you can interweave a number of gate operations that are there to do logical computations, and we add transport operations and then more gate operations. And so the sequence of all of that is essentially a quantum algorithm. So you do a gate, so you bring two ions together, and depending on the state of this ion, you do something to this ion, this qubit or ion. and so here, this is an example here, for example, a particular logical gate is if the state of the first qubit is 0, you do nothing to that second qubit, but if the state of this left ion here is 1, then you flip the state of the right ion. So if the right ion is 1, you make it 0. If the right ion is 0, you make it 1. That's what we call a C0 gate. And so here you can see like a quantum algorithm actually. A friend of mine from MIT, he's created this nice little simulation. You can see how these ions are moving around and come together to a gate, move away, and eventually we detect the state of the ion after computation. So this is a very simplistic quantum algorithm. Now, in ion quantum computing, people traditionally use laser beams, pairs of laser beams to execute these calculations. And that worked really well. In fact, people have whole developed workload in terms of using laser beams to execute gate operations. But this becomes a bit more complicated when you go to large qubit numbers, because then you suddenly would have to align essentially millions of laser beams, each with the accuracy of maybe hundredth of the width of a human hair. So imagine you have to build a machine where you have all these laser beams, and if you started aligning at this end of the machine, you probably over here, and then everything is misaligned over here again. So this is why people felt it might be difficult to build such a machine at scale. And so I kind of felt there's going to be a way how we get around this, and a better technology solution. And so this indeed there is, and so what we came up with at Sussex in 2016 is a different approach to quantum computing, where instead of using laser beams, you use microwave fields, and you use these microwave fields in such a way that you can now simply execute a calculation or execute a gate by applying a particular voltage to a microchip. And so the way that works is, and so I promise this is the most technical slide during my talk, so this is a little bit more complicated, but I feel that it's kind of useful to show you that. And the whole way this works is in the great company of engineers and engineering society, so I feel this is maybe nice to talk about, because essentially this is like a radio receiver. So I'm going to show you in a way why that is. You see up there again, so this array, this yellow lines, so this is this array of X junctions here, and the ions are levitating. Oops. Right, so you see, and so what I'm going to plot now here is the magnetic field. So I'm plotting here the magnetic field along this axis here. And because there's current carrying wires below the surface of the chip, we generate, using these current carrying wires, these strong magnetic field gradients just below each gate zone on the chip. And so why do we produce magnetic field gradients? In physics, there's an effect called the Zeeman effect. That it means the energy states of an atom or an ion move further apart as you apply a larger magnetic field. That's called the Zeeman effect. And so by essentially putting our ion in a different path, so by putting our ion in a different position here, now these states are affected by the magnetic field inside this magnetic field gradient. And you can see, so if I move the ion to a slightly different position, Z2 in this magnetic field gradient, it experiences a larger magnetic field. You can see these two states a little bit further apart now. So the energy separation is a little bit bigger. And an atom can only absorb microwaves if this energy separation here is exactly equal to the frequency to the microwaves that I apply. And see, you can see what happens now by applying these global microwave fields and by moving the ion in a particular position of the magnetic field gradient. I can essentially tune the ion by applying a voltage to either absorb these microwaves or to such another energy splitting that the ion can't absorb any microwaves. And so now what does that mean? If I now place the ion in a particular position Z2 by applying a voltage V2, remember I can move my ion, to change the position of the ion by applying a voltage. If I now move the ion to this particular position Z2, I can now tune the energy splitting so that the ion absorbs microwave fields and now executes a single qubit gate. Now equally, if I place two ions in yet another different position Z3 by applying a different voltage, that means now I've got two ions that can absorb these red microwave fields and now execute a 2-qubit gate. So making use of a magnetic field gradient, the Zeeman effect, and by me applying a voltage to a chip, I can now either choose to do nothing, to do like in the green scenario, sorry, here in the left, in the blue zone, or a single qubit gate or a 2-qubit gate. And the nice thing about this idea is that the number of radiation fields that I have to apply is not proportional to the number of ions. So for all other architectures, you needed more laser beams the more ions you have in order to do quantum computing. And that's a problem when you go to millions of ions. Here, the number of radiation fields does not scale with the number of qubits and the number of ions. So that means you can much rather easier scale this technology to really large qubit sizes. And the other big advantage is that we're using microwaves. And does anybody know, can somebody maybe speculate why microwaves are a very, very successful technology in that context? Anybody wants to guess?
Short wavelength.
Short wavelength, but where are microwaves used nowadays?
Oh, yeah, cooking.
Okay, good cooking is one thing. Something else you might have in your pocket right now? Exactly, mobile phones. So microwave technologies has been tremendously developed because of the use in mobile phone technology. So the electronics is really, really stable, very simply to manipulate. In stark contrast to lasers, where a piece of dust falling in a mirror will already affect the quality of the laser beam.
Can I ask a question?
Please.
The microwave fields, how many frequencies do you have? You said they were very stable, but how stable? You know, do they have to be low noise as well, low phase noise? You know, what are the limitations on the microwave fields? How many of them, low noise, both phase noise and jitter or whatever?
So essentially for each type of gate we need a set of microwave fields. So for example, if you have two ions, If you want to do a single qubit gate, sorry, if you have one ion, you want to do a single qubit gate, you might need 1 microwave frequency. If you have 2 ions, then I'm going to explain something which I'll talk about something which I haven't really explained. But if you want to do a 2 qubit gate, for each ion you need 2 frequency tones. It's called a Momo-Sorensen interaction. And so for a 2 qubit gate you need 4 tones, 4 microwave frequencies. In fact, sometimes you use RF and microwave frequencies. But that's a lot of subtle detail, which is not so important for your question. The second part of your question is how stable do these need to be, and how do you generate them? So you use what's called an arbitrary waveform generator. You can buy them from Keysight. You can order these things, and they generate actually like multiple frequencies digitally. So and the frequency stability and the noise characteristics, that is kind of the big advantage of microwave technology, because these boxes are so well developed that, I mean, we need amplitude stability, we need the frequency to be exact, but all of these things in commercial equipment is already much better than what we actually need to do. So one of the things that we're interested in is, for example, microwave amplification and things like how to reduce any kind of noise in microwave amplification. And so we work, for example, with industry partners to develop the right technology. But even there, it's not fundamentally difficult. It's just something that other people are so interested in. So we need to custom engineer that for our application.
Do you still have to use fault tolerant methodologies on top of using this microwave technique?
So the idea of fault tolerant methodology simply refers to the fact that each operation within a quantum computer has to have an error smaller than a certain threshold value, and that you use extra additional qubits in order to then account for and correct for the errors inside the operation. And that fault tolerant operating models you can do using any architecture, whether it's lasers, using microwaves. So what I'm explaining here is only the type of technology that we use in order to make fault tolerant quantum computing a reality. But there's many different ways you can also reduce the errors to the right size, the right magnitude.
Thank you.
Sorry,
Please.
can I go back a few minutes, really?
Yeah.
What you're describing, to me anyways, how to move all these arms around and change their state. But as soon as you talk about changing state, I think of ones and noughts, and you were talking about ones and noughts,
That's right.
which is back to old-fashioned what I understand. But are you saying that a one, in fact, is millions of states within that one?
No, that's a very good question. Thank you for asking that. So what I'm saying is that rather than being 0 or 1, the atom is 0 and 1. So one atom, so what I'm saying, let me translate this away from an atom and let me translate this to you. So what I'm saying is that you're sitting both here and over there. That's what I'm saying. And so that sounds very strange in our classical world, right? When I say that, you say, what do you mean? I'm one person, I can only be in one place. But that's only true in our classical world. In the idea of quantum physics is you have the idea of superposition. So an electron can go through 2 slits simultaneously and interfere with each other. Strange. So there's all these very strange things in quantum physics. And here, we make use of this principle of superposition, that the atom is now both 0 and 1.
All right, well, take that green ion in the middle there. Yeah, or any of them really, but take the green one.
The green,
Yes,
this
all right.
green line?
Or in your lower diagram, but yes.
Yep.
Now, is there another one that's the same somewhere else in a different state?
No, think of it this way. So let's look here. This is a good example of the green diagram. So the green diagram executes a single qubit gate. So I can spin down or spin up, or 0 and 1. So these errors are just a different way to represent a bit. And so now I want to prepare my ion in spin down. And now classically I could transfer it to spin up, right? So I could go from here to here, and we go to spin up or 1. And that's all classical, we all understand that. But what I can also do I can prepare this by applying a microwave field for, in fact, half the time. I can now prepare this atom using a single qubit gate in a superposition state where it is both spin down and spin up at the same time. And I do that exactly using this green field here. So by applying the microwave field for a certain amount of time, I can now prepare the ion that is being both in this one spin state and the other spin state, or like translating again what is a spin state. The electron is in two trajectories at the same time, in two energy states.
Right. Yeah, I think I've followed that.
Mm-hmm.
It's a question of how you get all the information out after that, these two states at once.
Alright, so that is I could talk about this for another hour, but let me try to compress another hour in one sentence. So basically one of the things I haven't had time to talk about and would take me a lot longer to explain is the nature of quantum algorithms. So what makes a quantum algorithm? How do quantum algorithms work? Because in quantum physics we also have measurement. And even for an atom can be in multiple states at the same time. As soon as we measure it, what happens is it collapses into one or the other state. And so that's why when you look at something, it is actually here or there. So when I look at you, you're going to be only sitting here, not over there. Only while I'm not looking at you, you might be in two different places at the same time. So that's a strange rules of quantum physics. Now, what we do when we design a quantum algorithm, we pick a quantum algorithm where essentially all these states interfere in such a way that all these numbers that are computed give rise to a single answer. So that's the way how quantum algorithms are written, that they conquer certain questions where you have to do lots of calculations to get one answer. So let me give you an example to make this a little bit more tangible. So take a sine function. So if I would give you a black box, and if I draw a sine function, I have to evaluate this sine function in a lot of places in order to draw that sine function, right? And if I've drawn it sufficiently long, so if I've evaluated that black box function that is a sine function many times enough, I can derive the period of the sine function. So imagine if I give you a black box and I'm asking you, I don't care about the evaluations of what this black box function is being evaluated, I just need the period. Then that's a kind of typical problem where a quantum computer is very powerful, because even during the calculation, all these numbers are actually doing something. The final answer of the quantum algorithm is only one number, that's the period. But you couldn't get to that period classically without evaluating that function in all these different places. And so this is kind of an example of feel-good example of how you create a quantum algorithm. It's essentially, you don't think of a quantum computer just as a super powerful machine that can just solve everything better, and you just run Windows and suddenly you have the super mega clock speed and that's it. So it's unfortunately a lot more complicated. So you don't just have to build the hardware, you also have to make the software. And the software has to essentially capitalize on the strengths of quantum physics without compromising the fact that when you measure, then the quantum state collapses and you actually only get one answer. But that answer may well depend on all the calculations, and that's where the key sits. So the answer may depend on all these calculations. You had a question.
Yes, I have a question, because you mentioned about superpositions, and when you observe said atom, it will collapse into either one of the two states, right? Is the probability between collapsing into either one of the two states equal? Or
so that's described by what we call the amplitude of the wave function. So the square of that is the probability of you taking a 0, 1. So usually I write a quantum state as alpha 0 plus beta times 1, and alpha squared plus beta squared, they are the normalized magnitudes of these states. And they essentially then correspond to probabilities of me observing in one or the other state. And so that's where then I'm going to write out the quantum state with lots of atoms, and it's going to be a big thing. That actually makes it also very hard to calculate classically, because it's essentially a big matrix calculations that are very big to get around the hand. Yeah?
Can you do dynamical decoupling with global microwave fields?
Absolutely.
Wow.
So we've written a whole paper on that, so actually it's on our website. So, yeah.
Yes, you mentioned about errors, and you hinted earlier on about these things being deep in minds. Is cosmic ray a thing that could be more powerful than what you're putting in there, and not for a stage out?
So that's a very good question, and indeed, cosmic rays knock out entirely the quantum state for superconducting qubits. They don't affect trapped ions at all. So that's the good news.
Okay.
So that superconducting qubits are affected by that in such a way that they produce what's called a correlated error, which is kind of poison in quantum computing. So that's why that also makes superconducting qubits more challenging to develop, to scale, because they're affected by it.
It wouldn't affect this technology.
Sorry?
It wouldn't affect this
Not
technology.
at all.
Just the
So
super.
that's one of the nice advantages.
I was going to say otherwise run it at night.
There's still cosmic rays there too. Good, but let me move on, because obviously I want to show you some of the kind of exciting breakthroughs that we've made recently. And so, so one of the things we talked about, that you need a lot of qubits in order to do useful calculations. And the problem is that a single chip can only hold so many quantum bits. Because fundamentally, like, a chip maybe can be the size of a commercial wafer, but even a commercial wafer is only so much size, and you're not going to fit 1 million trapped ions onto one wafer. And so in quantum computing, you have to have some type of modular setup. So modular setup where you can then have multiple chips, each hosting lots of qubits, and you have to now connect these modules, these different chips together. And so the question is now, how can you make a trapped ion quantum computer modular in order to allow for sufficiently many qubits so you can solve some of these really interesting problems. And maybe the traditional way that has been worked on for many years is represented by this diagram here. As you can see, these quantum computing modules here. Each one of them is a quantum computing module, and they're connected via optical fibers to detectors. And so this is the idea of photonic interconnects, to couple fibers. The world record for this technology is held at Oxford University, and they managed to get the connection speed between adjacent modules of 180 connections per second with a fidelity of 94%. And so fidelity is one minus fidelity is the error, so it means there's a 6% error. And you can see that speed is not very fast, and also the error is quite significant. And this is really tremendously difficult to develop technology, unbelievably difficult. So over 20 years, when I started in this field in 2001, Chris Monroe and the group I worked then already developed this technology, and it's still not that far advanced. So I thought to myself, I want to build a quantum computer. This is not a technology that would allow us to scale. And so in 2017, we proposed a different way to make quantum computers modular. And so the idea is here to use electric field links between different microchips, and to then simply transport an ion from one chip to the adjacent chip. And at that point in time, it was an idea. People were skeptical about this idea, but it can be done. And so whenever somebody tells me he can't do something, I'm straight on it. And so we said we built an experiment to actually demonstrate that exactly can be done. And so the advantage of that technology is very straightforward. First of all, it's very simple engineering. You can see if you compare this picture here, where you simply shape the electrodes at the edge. You can see you have lots of different connection points between these chips. It's very different than having something like that with these optical fibers going to detectors. So simplicity is already a big advantage, but the connection speed that you can achieve is also very, very significant for the practical operation.
Winfried, back in that picture of the different modules coming together, where are the microwaves emitted from?
So what we use here is a technique of global microwave fields, And so essentially you can just have a microwave emitter and antenna, either internal or external to the vacuum system, and it just emits microwaves everywhere. Because remember, like the microwaves are everywhere, but the ions, just like radio receivers, can only absorb these microwaves if they're exactly in a particular position within the magnetic field gradient.
Well, I'm wondering if a good analogy is like a phased array antenna used in cellular systems today, where you have multiple emitters basically creating the field by interacting differently. Is it a good analogy, or?
It's overcomplicated, so we don't need that. So we can just, you could have think of it, you could even have a single microwave for an outside vacuum system. That would work. Okay. It would not work so well because when you get interference, the microwave amplitudes wouldn't be exactly everywhere the same. So in one zone, a gate may take longer than the other zone. So having reasonably homogeneous microwave intensity across the chip is useful, and that's obviously something what such an array would do really well. So we are interested in that technology, but it's by no means required. It essentially enhances the clock speed a little bit, because if you think about it, if all these operations happen in parallel, where the operation is the slowest, because everything happens in sync, like in a computer, it's clock cycles. So the slowest part, everybody else has to wait for the slowest. And so that's kind of why a means to use radar technology to have a more homogeneous coverage of microwaves is useful, but actually not required. So we then set out to build a machine like that. And so this is a picture of two microchips, one chip here and one chip here, and they're connected. There's a little gap here. And so now let's look what we've managed to do. So instead of achieving a speed of 180 per second, we managed to get a speed of 2,400 per second. And instead of 94%, we managed to get 99. I'll have to say these numbers, that's right. 99.9999993%. So that's really, really, first time around, there's a lot of things we can improve on the setup, which we're in the process of doing now. We increase the speeds by 1 or 2 orders of magnitude, and the fidelity by probably 7 or 8 orders of magnitude. So it's really, you can see this is really a step change towards building large-scale quantum computers, because we have the numbers already sufficient for to run quantum computing. And maybe if you're interested in the subtle parts of the technology, this was actually only limited by the speed of the DACs, of the digital to analog converters we used, and the filtering circuits inside the vacuum. So we have now exchanged these, and we think we can increase this speed yet by another order of magnitude. So you can really see this is sounds quite positive, and so this is a movie where you can see where you see it happening. So you start the ion moves here, and so this is the first chip here, and eventually the PS here, and it's going over and over again. In fact, what this ion does is more impressive than what I do every weekend. I usually run 8 kilometers on a Sunday, and this ion actually runs 10 kilometers. And back and forth, you can imagine how many times the ion goes back and forth in order to get to this tremendous success rate. In order to even sample that, we had to move the ion for over and over, back and forth, and it just has not been lost. This is a very, very reliable technique. And in physicists in the audience, I should also mention that we measure the coherence of the atom, and we cannot even measure any loss of coherence. So this is also extremely exciting. So there's basically no measurable error in the transport process. So let me make a step back again and show you kind of the bigger picture now, how this comes together. So in 2017, we released a blueprint of how you go about building a 1 million qubit quantum computer. It was a collaboration with Google, Riken, Arbus, and Siegen University. And so part of this plan, this blueprint, is this X junction geometry, X-junction geometry, and you can see a microchip from our lab where we have such an X-junction geometry. And so you have this quantum computing module here. So right on the top surface you have all these X-junctions, all these electrodes, and the ions are levitating above the surface of this X-junction. And below here is all the electronics, all the digital to analog converters that generate the voltages for each of the electrodes. And I should say this is kind of how this thing scales. So the more ions you have, the more electrodes you need, and the more decks you need. So that's something which grows, obviously, when we have more and more qubits, but this is kind of how you want it to grow, which is obviously a normal computer processor also grows by adding more and more transistors. So it's very similar here. And so obviously there's a lot of dissipation, there's a lot of electronics in a very small space, so we need a lot of cooling power. And so you have these microchannel coolers here integrated, and all you have electronics to calculate the actual voltages that you need. And so with that, I want to just show you, this is a classical computer architecture. We also have this multi-layer architecture. The only thing that's different here between these, I shouldn't say the only thing, but what's markedly different here is that everything's a little bit larger here. But that's okay, because quantum computers don't need to be small. Nobody needs a small quantum computer necessarily. You use a quantum computer for its computational power, and you compare that to a supercomputer that might fill a whole warehouse. So this is a film to show you a little bit how all of it comes together. So you start with an ion in the entanglement, so in the loading zone. So you have two ion species, one that cools the second ion. Now you bring these two ions together into the gate zone. Now you making use of these current carrying wires below the surface, you generate a magnetic field gradient, and now using these global microwave fields, you have done a quantum gate between ion 1 and ion 2, and now you can move the ion somewhere else. For example, if you wanted to measure the outcome of this computation of this gate, you could now detect. We do still use some laser beams, but these are what's called global laser beams. Go across the whole architecture to where one beam may interact with hundreds or thousands of ions. And so here you can see what actually happens now. So all these things happen in parallel, all these shuttling operations, gate operations. Kind of looks like a game of Pac-Man, really. And this is the execution of a quantum algorithm. And now this is as big as you can fit on a single module. And so now this is one of these modules, and you place one of these modules simply on top of a frame, and by placing in a second module next to it, and by moving the module with respect to each other, you can now align these. Now, if you haven't aligned it well enough, the electric field lines don't connect. You can't transport the ions across. But if you move them and align them well enough, then you can simply transport the ions to the other module. You can see that goes all in parallel now. So this is really powerful. The bandwidth of transmitting quantum information from one module to the other is heavily parallelized. And you have all these pathways that all happen in parallel. And so this is going to be the artist's impression of what a quantum computer looks like. So there's this big array of microchips connected together, and depending on the problem you want to solve, you can just add more and more of these quantum computing modules in order to then work with more and more quantum bits. So how do we go about actually building quantum computers? And so we started this process at the University of Sussex, but the university can't really complete some of the really heavy lifting engineering that we require in order to build practical quantum computers. So we started a company in 2018 called Universal Quantum, and the company is located actually very, very close to Brighton and Havelsheath in Hamburg in Germany. And so the idea really is to do some of the really heavy lifting fab tasks that you could never pay as a university, to work with big foundries to make these chips well enough. So this is a company we're very proud of. Our investors as well has really helped. So investors are from all across the world, and for someone in Hoxton, for example, has given rise either use a lot to deliver road. So there's a lot of other really amazing investors who really helped us, not just with the money, but also with bringing the right people, the right engineers to help us build machines like that. So we've been awarded the Institute of Physics as a startup award last year. So we've been really proud that the Institute of Physics recognized us, and Bloomberg identified us as one of the top 25 UK startups to watch. So that was a kind of a funny thing, because not just where we are, but also OnlyFans and some other. That's a bit strange to be in the same as that. But so what? Now we're working together with creating a whole subsystems development together with a lot of subsystem developers in order to do this. We don't want to do a lot of the work ourselves. There's a lot of amazing companies out there who can really help, and so this is somehow the ecosystem we try to generate. So we work with Rolls-Royce on developing quantum computing useful to develop more fuel-efficient aircraft engines. So that's really useful to work with a user. We work with semiconductor companies like ARM or Semivice or others on chip fabrication. We work with software companies, with universities, with electronic companies here in the area with Atlas Vacuum, to really kind of generate a whole ecosystem here in the region. So this is something really exciting. I'm going to say a few more things about that at the end. So we've, a couple of years ago, we started a subsidiary in Germany, obviously after Brexit. That's a more timely thing than to do before, and really proud to say that recently we've been awarded the largest quantum computing contract ever awarded to a single company by the German Space Agency to build 2 quantum computers in Hamburg based on that very technology I've told you about today. So that's really, really exciting that our technology has been recognized in that way. So the way as a company we are different to other companies like what you've probably heard of is the way we execute gates. So this is using voltage as applied to a microchip rather than using laser beams. Our operating temperature is only requires mild cooling rather than absolute zero. The modularity, as I explained, is done using electric field links, and all of this is done using a silicon microchip platform. So I think with that, there's probably a good time to end, and obviously there's millions of things I haven't had a chance to talk about in this lecture. As I said, I love questions. I was happy that you guys already asked a lot of really, really amazing questions. So quantum computers are a long-term game. It's not something that you will have in a couple of years. This is really hard technology which will take time. But because it's so exciting, because it's so disruptive, it's well worth to really engage with this and actually try something what a lot of people felt would be impossible to achieve. And the way we do that is using microwave technology, which again is something which is really scalable and really works in a way that you can really imagine building such a machine. Now, before I end, maybe I should also say if you're interested to work on this technology, then you actually have a very special place here. So the University of Sussex is the first university in the world that is now offering an undergraduate degree where you can be exposed to research from your first day of study in your undergraduate. So normally you'll do an undergraduate degree in physics, and after 4 years, if you get high enough marks, you can then be engaged with a PhD. At Sussex, we've changing this, so we have a mini undergraduate degree. We are exposed already from year 1 in research, and that enables you really to understand a little bit better why you're doing some of the really tough, difficult math in your undergrad, because you can do really amazing stuff like quantum computing later. So we're not just that. At Sussex, we also offer the first online master's degree in quantum technologies. So if you're not interested to do a traditional degree, but you kind of want to expand your horizon a little bit, then when you're on time, at home, wherever you're located, you can do a master's in quantum technologies. You also have a traditional MSc degree in quantum technologies. And if you've done your undergrad degree, you want to do a PhD. Here in Sussex, we have a big research center, Sussex Center for Quantum Technologies, where you can engage in research across all the different quantum technologies. And I'm heading a research group that works on developing quantum computers. So, so that's also a way how you can engage with that. But I think now is a good time to stop. So thank you very much for your attention.
Fascinating. Lovely.
Yep.
A couple of questions. Who does your silicon foundry and who's doing your prototype chips at the moment?
So we have two different approaches. So in the research group at Sussex, we use university clean room, university clean facilities like PhD students go and very big chips. And you can imagine the chips which are made like that, they're not very, can't be scaled up. So they are not, they're good for trying and playing with things, but they're not good for building real devices. But the company works with foundries, and so we work with a number of foundries. That is commercially sensitive, so I can't actually talk about which foundries there are. But essentially, you can imagine, there's not that many foundries, so you can probably smartly guess at least one or four.
Right. Just looking ahead, how many years do you reckon it will be before we have quantum computers which are room temperature, desktop, laptop, mobile phone?
Right. So I'm dreamt all my life and all my career, and when I started, now for me, the school of quantum computers get hundreds of websites, and everybody has some opinion about quantum computers. When I started, everybody said it's completely impossible, you can't do quantum computers. And whenever somebody tells me, as I said, remark before, you can't do something, it started in high school already, I'm straight on this. So that's in 2001 I started building quantum computers. So my dream was always to build a quantum computer that can create new pharmaceuticals. I want to, when I'm dead, I want to be able to say I've built a machine that can really help humanity. That is all I care about. I don't care about how big that machine is. So originally, in 2017, when we published this blueprint, we predict Nature ran a news story, and the title of the headline of this news story was "Physicists Propose Football Pitch-Sized Quantum Computer." And at that point in time, our blueprint literally felt it would be essentially like a conventional supercomputer. Now, we've done a lot of theories in the last years, and now that same machine is going to be 2.5 meters times 2.5 meters. Now, that's really, really exciting. Exciting in the sense that because we need less qubits, everything is a little bit more compact. But realistically, to build a quantum computer that maybe can tackle some of these really interesting applications, you probably look in 5 or 10 years. There's not going to be one day you're going to have early applications that happen maybe a little bit earlier. Other applications that are really difficult. For example, a couple of years ago, we wrote a paper on how quantum computers could write Bitcoin encryption. That's actually really hard. That won't be the first thing that quantum computers do. But how, these machines also, I should be clear, are not room temperature. They're cooled to liquid nitrogen temperature, 70 Kelvin. Actually has nothing to do with the quantum physics. It has to do with the fact that silicon is a better heat conductor at 70 Kelvin. It allows us to take the heat of all the classical electronics away much faster, which is really important. So for me, it's never been a big thing to make quantum computers small or to make them room temperature. I just want to have one, which can tackle some of these really interesting problems. I would certainly say you're not going to have a desktop quantum computer that can do something useful anytime soon, and so it's at least plus 15 years plus. Now, if you find anybody who can predict the future even reliably over a period of 5 years, I'm already very impressed, and you probably won't find anybody generally. So predicting anything beyond 10 or 15 years is ridiculous. But to be honest, I mean, I felt it's never that exciting because you're going to run these machines via cloud. So you're going to sit on your laptop at home, you're going to log into a quantum computer. You can already do that today. Only the quantum computer you can log into today is pretty terrible. But essentially you can already log into these machines, you can run a computation, and you don't actually want that quantum computer at home. Because the electricity bill will be quite substantial.
But might it be Moore's law all over again?
There will be some kind of Moore's law. So that's the other important thing. A lot of people ask me, so when will we have a quantum computer? And if you were to work across campus, there's already 5 quantum computers there. But these quantum computers can't actually do anything sensible. So they're just small technology machines that with which we develop some of the underlying processes within the quantum computer. So there will be a first quantum computer that can really tackle a really interesting application, and then a couple of years later, the quantum computer will tackle another interesting applications. And so the reason why a lot of companies and other stakeholders want to work very early with quantum computing developers, because by us understanding exactly where the value sits in the application, we can streamline these machines for particular applications maybe come online a little bit earlier. And that is obviously very interesting because these technologies are disruptive. Disruptive means very similar to Google search algorithm. I'm sure you now, you probably like me, use Yahoo and other very strange sounding search engines at some stage, and then we stopped because it disappeared because they were not as good as Google. And so that's very similar.
Thank you. We got one there. Did you want to ask a question? You will raise your hand earlier. Okay. Dan?
So in terms of scaling, what's next for your ion trap design? Will there be some, you showed a classical CPU there with different layers. Is another dimension coming into your scaling at some point? I'm sure you thought about it.
A lot of people say that. And honestly, coming back to this gentleman's question here, can you make these smaller? Imagine if you were to fold them, and they would already be a lot smaller, right? Right now, I'm saying there's going to be one big plane. You could just fold them, and that would make them smaller.
So you could bring more efficient. Like, could you move traps from between different? Sorry, could you move ions between different layers, and therefore you could have. It's not just about size; it's about efficiency of operation and number of operations.
So this is always the answer. The principle is absolutely yes. Yeah. In practice, you pick your poison. So essentially, like, we have a whole team of engineers, and kind of like they have to constrain certain things, and then they put something else. And you can always work hard on one thing that makes another thing easier, and vice versa. But right now, as I said before, we're not so concerned about the actual size of the machine or a lot of the kind of standard operating procedures. We just want to build a machine that actually tackles one of these problems. And then after that, we're going to think about things like maybe making them more space efficient by folding them over, by doing things. But some of these folding operations will require quite significant engineering. And right now, our engineers have their hands full with doing engineering for a simplistic solution. But you're absolutely right. As soon as the first machine is built, and the next machine will have some of the modifications that make it a little bit more efficient in many different ways. And I could speak of hours of plans we have to do that. And some of these things are very technical. Some of these things are very simple, like, for example, this thing about folding a machine like that. But yeah, it's a whole array of things. But we also have to be patient. So everything takes time, and so we have to, do things step by step. And everything what I showed you today sounds really exciting. But what I haven't shown you is all the failures and all the things, all the lasers that are breaking and all the chips that explode. I could tell you stories like that. So all that happens, and everything just takes time, and so that, which is fine. So you just have to be patient, and that's why when the time scales come.
Okay. A question about patents. Mm-hmm. And I imagine some of your backers are very interested in commercial aspects and so on, mm-hmm. and would like to keep things secret. So what is the balance of patents versus openness in your work?
Oh yeah, that's a pretty loaded question, a difficult question. So when we published this blueprint, we purposely didn't want to patent it. Because first of all, we felt like these ideas are so powerful that we shouldn't prevent others from executing on them, because the technology is more important than maybe our financial benefit. But now that we have investors, these investors, in fact, we have more investors and we have more people investing in us, we need a patent portfolio. So now as a company, we patent lots and lots of different things, technology aspects of this technology, of this stuff. Sometimes we collaborate with others, and when we do so, we maybe have we have an agreement that neither of us will patent, and we enable the whole community to benefit. So that's also an operating model which allows us, for example, to work with people where otherwise we spend the rest of our lives with lawyers trying to somehow figure things out, and so then we just go ahead and say, look, let's make this available for everybody. So there's